Hello, c'est Jean-Marc from MilliBox, and today we want to talk about low frequency testing. Now, low frequency is not that low. We are in millimeter wave and sub-Tera. So when we're talking about low frequency, we're talking about 6 gigahertz to 18 gigahertz. Namely, we're talking X-band and Ku band. So it's still very high up there, but it's lower than our spec. Our spec is 18 gigahertz to 330 gigahertz. And that's where we have absorbers performing at 50 dB of attenuation, which for those bands is really good. But what happens when you go to lower frequency? That's a question that our customers are wondering. They would like to be able to extend their project coverage with MilliBox to X-band and Ku band. So there are a number of considerations. For one, we want to know the absorber performance. And we check with the manufacturer of the absorbers, and they tell us that the absorber raised from 35 at 6 gigahertz to 50 at 18. Still pretty good, but we don't recommend it for bands like 2.4 or 5.2, where the interference in those spectrum is way too high. But for band over 6 gigahertz, still gonna give us a pretty good attenuation and really good consistency in terms of measurement. Second consideration is the size of the DUT. As the frequency lowers, the DUT tends to get bigger. And we have positioners as big as able to carry 38 centimeters of width of a DUT. That's 15 inches. So that's the first question. Second question is the far field distance. We are testing, most of our implementation are in direct far field. So for that, with our modular design, we can access to a far field distance up to nearly 3 meters. If your project fits in those metrics, MilliBox could be a great fit for your testing purpose. Now we want to go one step further, and we acquired X-band standard gain horn of 10 dBi, and we put it on the bench as a DUT, and we are going to measure it. We got the data from the manufacturer to tell us for each half gigahertz of frequency, all the radiation patterns that they obtain. And we are going to measure it right now and check if we have a good correlation between the manufacturer's data and the measurement with MilliBox. And that will give us a better confidence whether we can use MilliBox for X-band or Ku band. So let's do some capture. And then we'll do the correlation. Yeah, so as we discussed, we have a WR112 reference horn, 10 dBi of gain that we put as a DUT. We are going to do a 3D radiation pattern for it. We do a surface plot, and we do it from minus 40, plus 40 in azimuth and in elevation. With a step size of 4 degrees, and this is a test. And we'll do it at 9. We'll monitor 9 gigahertz, which is the middle, and we'll use the hardware trigger, which is a new feature that we'll introduce soon. So stay tuned for that announcement. And now we're starting the collection of the 3D data for this reference horn. As you can see, we're using the faster synchronous trigger feature, and then we're doing the acquisition. We can monitor here our progress. So we're extracting the trace directly from the VNA that we connected. It's 420 20 gigahertz VNA that we have directly connected to the our reference horn on one side and the measurement horn. Our measurement horn is a dual reach wideband horn. So here we're doing that measurement. You see the lobe is creating very nicely and quickly. So that's nice. So we'll collect that information. Here we have in our trace, as you can see, we have 22 points. 22 points from 6 gigahertz to 12 gigahertz. That makes that we have the number of points that we need. You know, like we have points every 0.5 gigahertz, like 500 megahertz between points. So we're doing 13 radiation pattern in one shot. Then we'll use that to do our correlation. So when we close this, then we see rendering in 3D. Of course, it's nice, look perfect, no issues there. And we're gonna expand that to all the 13 radiation pattern that we have, and then we'll do the HV collection of data, and then we'll compare that to the datasheet from the manufacturer. Right, so here we are doing E-plane, H-plane plot, so an acquisition. So we are starting at minus 90, plus 90, and we do at 2 degrees of resolution. And we plot at 9 gigahertz, and then we're now using the trigger. So let's see how it looks. So that's the way we're going to do for the entire band, probably at higher resolution than that, and so that we can compare the result with the manufacturer data. So we are sweeping in azimuth. We're nearly halfway there. It's rendering very nice. Past 75 degrees, we start seeing noises, but the rest is pretty clean. Let's see on the V, on the elevation side, we are still at 2 degrees of resolution. From minus 90 degrees to plus 90 plus 90 degrees. And we're showing at 9 gigahertz, but we're actually capturing all 13 radiation pattern in the background. Since we're collecting the trace directly from the VNA, the entire trace. It's nice too. It's very smooth, very clean. And the doors are open. I mean, that's something we have to consider, but I cannot show you if I close the door, so I have to make some compromise. Yeah, very nice. A little bit of shoulders, but not much. Okay. So now we have the data that we can correlate. So now that we capture all the data and we have the data from the manufacturer, we can start comparing for each frequency whether we have a matching correlation. So out of our little experiment, we could collect some interesting data, and then based on the manufacturer's information, we can start seeing some correlation or not between the measurements. So we start at 6 gigahertz. You see, the datasheet data is a little bit unstable. I mean, a little bit awkward. So, but still, we can notice some shoulders position at the right. And some features, you know, like the shoulders and the peak and valleys, we are trying to see if they match per angle and per power level, right? So here you see you're trying to detect some features, like for example here at 10 gigahertz, you know, you see these those strong side lobes that are only present in elevation and nearly completely absent in azimuth. And then we see the same thing from the datasheet, and clearly shows, and the levels are about the same here and there, even though it starts getting close to the noise and at very wide angle. So even though we have strong correlation at the on the main lobe, and that's kind of expected, we still see that the side features and the side lobe and the level difference are matching in degrees and in power level, right? And that's what we are looking like. This one is a perfect example as well, where we have features of the radiation that can be easily recognized in terms of position, in angular position, and in power level. And that's what we're expecting. So you see those down there, here. The colors are kind of inverted, but that's kind of what it is. So, and here when you overlay them, but still they are showing strong matching. Here too, here we are 12. That's getting very strong as well. With the feature clearly overlapping. So as you can see in that experiment, we had some pretty good correlation. We used an MBX32 and a Gimbal 4 300, but there are many more models that you can discover on our website. So if you have some project in X-band and KU band and you're considering using MilliBox, that's certainly a strong contender, given the affordability, modularity, and all the features that we regularly talk about. So MilliBox is fine for those frequencies. Don't hesitate to contact us. Thank you so much, and talk to you later.